Hello, this is a demo for the software that we developed for data mining class at University of Oklahoma and fall 2015. And all the software and data are in this folder. And the software that we developed is to do a classification for lithology using proximal support vector machine on seismic data. And as we go in here and we can find out the actual data and the GUI in this folder called main program. And first thing, since we're using MPI in this program, the first thing we need to run this script as administrator to enable the MPI on this computer. And after finish, just quit and start the GUI. And so here is the GUI, and we can monitor all the process in the command line window. And there are 5 parts or 5 modules in the GUI. The first is format conversion, in which we convert the seg-y format data, which is a commonly used format in exploration geophysics, to a simpler format that we can work on. So let's start from step 1 to convert the data. And here we need to use this 5 files, which are 5 seismic attributes, as input. So we need to convert all these 5 files to the .h format. And let's do that one by one. And we just give a name, we just rename it as the same. But in here we need to give it an extension called .h, and project names are data mining. And all those header things we can view here to see all the header locations, and it's the same as default. And here the vertical unit in this data is kilofeet. So hit execute and we'll convert the data volume. And we do the same thing for the second. Okay, after all the files are converted, we can then view one of the files. And here I choose the P-wave impedance. And all those things are actually different formations in the subsurface. So we want to classify on those formations whether this is shale or non-shale. Then the next step would be test our classifier. Here I just provided 2 sets, one called train 1, one is the test 1, to test our classifier. And just give a name and suffix, let's see, GUI demo. And then header lines to skip is how many header lines in the file, and here we actually have 0. And data dimension, we have 5 attributes, there are 5 columns of data, and number of classes, we have only 2 labels, with 1 for shale and 2 for non-shale, so 2. And running mode is testing, and we can also run as a cross-validation. And in this case, we only use 1 file and take let's say 10% of the data to do the cross-validation, use as a validation set. And for illustration, we only run it as testing, which is more quicker. And here, how many percent we use to run a PSVM algorithm. And typically, we can choose a pretty small number of that. And in this case, we choose 20%, and which will run in several seconds or less than a minute, I would say. And then we'll do a classification on test on the test 1 set, and you will see the accuracy is around 73%. And here I also I only use the default values for the parameters. Okay, let's move to the step 3, where we can apply to the whole volume. And in this case, we have a prepared data set called train funnel, where we combine all our training data and do a subsetting in the training data. And here we took the 5 input attributes and one thing we need to pay special attention to is those input attributes should be in the same order as they lie in the input file. And so here is attribute 1, in the second column is attribute 2, and here is attribute 3, things like that. So we have to make them in the same order. And surface still GUI test. And okay, so the primary parameters will be similar to the parameters here, and no header lines, 5 attribute and 2 class, and default parameters. And here let's say 50, no, maybe a smaller number just for the illustration purpose. And in the operation window, we can define whether using a time window or using the window defined by 2 horizons, which are geologic formations. So which we wanted to bound our analysis in a certain level. So here's top horizon, here's bottom horizon, and the file type is here, and everything looks good. And in the parallelization parameters, here we can automatically determine how many processors are there on this machine. Then we will go back to the primary parameters to start the program, and it will take quite a bit of time. And that's why I just want to show how it looked like when doing the calculation, and then we will move to the result that I generated previously. Now let's go back to the data format conversion to convert the previously generated result back to our .h file, and we'll change the name to, let's say, facies, and the header location in this case is different, so I'll type in and wait the conversion to complete. Now the result is converted successfully. Then we go to the data viewer to actually look at the result, and the name would be facies, yeah, this one. And I'll change the data range of here. Since we only have 2 values, we make the minimum as 0 and maximum as 2, and we change the color table to rainbow. And now you see all those green colors are our shell, and the purple colors are classified as non-shell. And the final step would be convert this. We assume this is the result that we just generated, and we will convert this back to sec_y. And here we use, and further up we will input this data to a commercial seismic interpretation software. We want to make it at 77, 5, and 21, so that the other software can read it in easily. The final step would be look at the data in a commercial interpretation package, and here I used Petrel from Schlumberger to do the visualization, and want to import the data that we just generated. Okay, so now this is our data. Red is for shale and yellow is for non-shale. And that's all I have, and thank you for watching.